So what we have been doing, we are dealing with the first order circuits, and what we have done, what it is, mathematical model of the first order circuits, which is called the state equation. It is a first order differential equation. So once you wrote this equation, you're going to solve it, and solution, we said there's two alternatives. One of them is the mathematical one, which is seen in the differential equation course, which includes two parts of it. Let me go in. Mathematical solution of serial RL circuit. Solution has got two parts. Homogeneous solution, particular solution, general solution. General solution is the summation of those two solutions. We have done all that. But we have considered the DC source as an independent voltage source. Now we are saying what will change if you change this independent voltage source mathematical structure to AC source, sinusoidal signal. What happens? So we would like to see that. Why we are examining those two independent sources specially? Because DC source is the battery one. So all the electronic circuits have got a DC source. Consider your telephones, consider automobiles. These are all DC driven equipments. And there are many equipments that we use in our houses which is powered by the AC sources, the ones that we use in our houses. That's why we are examining two different sources drives these circuits. So what happens if this independent source is an AC source, has been examined in this frame. So here you are. That's the mathematical solution of a serial RLC circuit with AC source. The previous one is DC, where the previous one was DC source driven. Now this is AC source driven. So what we are going to do in general, we are going to find the particular solution, homogeneous solution first, as we do it in differential equation courses, and homogeneous solution. But this is in Turkish. I removed that. So immediately let me to remove that. Make it in English. One. Here are. This is the English one. Homogeneous solution, particular solution, and the general solution. So addition of those two gives you the general solution. So how we are going to calculate it? I am going to do it by hand as I do it as on the board in class. In general, I could say that the particular solution is not going to change, whether it is AC source or DC source. Why is that? Because if it is homogeneous solution is the differential equation when the independent source is equal to 0. So that means homogeneous solution do not depend on the source, whether it is DC or AC. That's why the homogeneous solution is not going to change, but particular solution is definitely is going to change. So let's see this now. Here are. This is our serial RL circuits that we are going to examine. In this circuit, our source is an AC source, we said. That means Vs is equal A times small a cosine omega t plus phi. Just remind you, a sinusoidal function, this is a mathematical, That's a mathematical function, isn't it? So this is a sinusoidal function, it is said. This sinusoidal function has got three parameters in it. Let me to make it different color. So this is one parameter, that's the another parameter, this is the third parameter. That t is time and it is an independent variable. That is dependent variable. The voltage changes with this. So if you draw this function t vt, it's going to be something like that. So that a is this a. That omega, so you know in mathematics that's a periodic function. That's the period. That means this part is repeated. So this time interval for one period is that t. So in 1 second, how many capital T's are included is the frequency. 2p, that's the frequency, multiplied by 2p gives you that angular frequency. That omega is this, that omega. Okay. So what we are saying now, we've got this circuit. We have examined this circuit before. For a DC source, it was Vs is equal 100 volt. So we are not going to examine this one. We are going to examine the circuit now when the source is AC source. So what we've got is the differential equation represents this behavior of this circuit is this. dIL over dt, that is inductor's current, equal is minus R over L e to the power, sorry, that's going to make a mistake, my memory that is, minus R over L IL plus 1 over L, so that's going to be L. Vs. That's the differential equation. How we are going to solve this? As we do it in mathematics, we are going to repeat some of the things. The first one is find the homogeneous solution. Homogeneous solution. What it was, remind you, this differential equation, when Vs equal to 0, that means known function is 0, solution of this differential equation is called homogeneous solution. What is the difference? That means Vs assumed equal to 0 in this equation, and make the equation is like that. How we are going to find it? As you remember, we are going to estimate that IL homogeneous, homi right here, is equal C times e to the power st. So this is an estimation of a solution. If we can calculate these two parameters here, C and S, then that means we found the homogeneous solution. So if you remember it, you can read the previous example that we have done. How we calculate that S, that is characteristic root, you can get S equal to minus R over L. That's the coefficient that IL in this equation. So we found S, then I homogeneous solution L is equal C times e to the power minus R over LT. Calculation of that C will be done later on by using this uh, initial condition. So calculation of that C here is going to be made by this data given to us with the circuit. That's the initial condition of the inductor when t equal to 0. So that's the first part of it. Whether it is a DC source or AC source, that homogeneous solution format is the same as this. Okay. So what we'll do next for the solution of a circuit like that is to calculate the particular solution. So next step is the particular solution. So remember what is this solution is. It is a source type of function. It's going to be a source type function. What does this mean? The source is a sinusoidal function, so particular solution is going to be a sinusoidal function. In order to determine a sinusoidal function, you've got to calculate these three parameters, 1, 2, 3. Rest of it is known, isn't it? That's why we are saying the same type, source type of function. It's going to be that particular solution. On the other hand, this particular solution should be the solution of this differential equation. What does this mean? If you replace your solution, substitute for the IL in this equation, left hand side must be equal to right hand side. So we are going to do this similar operation that we've done for the homogeneous solution case. We are going to estimate that source type of function. So assume that this source type of function is IL particular is capital A, not the small a, capital A, cos omega t plus theta. So this function, particular solution, is the same type of the source function. The parameter which is called the magnitude is different. In the source it is small a, in the solution it is capital A. Cosine function, it's a sinusoidal function. Mathematically it can be proved, but we are not going to prove it here. We know that source frequency is going to be the same as the particular solution frequency. That means this is going to be already found. And then we are going to, this is the angle or the phase. Maybe I have forgotten to say that phi is the angle or the phase which determines the beginning of your function. So this in here, in this estimated function, it is theta. So as I said before, we said in order to determine a sinusoidal function, there are three parameters that you've got to know. And we are saying now one of these parameters we did not to calculate because it is not going to change. And the other parameters is the magnitude and the phase. So we are going to calculate these two things here, that A and that theta, in terms of the circuit parameters. So how we are going to do it? We said if we substitute this function in the differential equation, left hand side becomes right hand side. So let's do it then. So we're going to take the derivative of this function. So I'm doing this now. So derivative of this function is a times, maybe blue one is better for the calculation of particular solution. So derivative a times omega sine omega t plus theta, and in front of it must be minus. Derivative of cosine is minus sin, isn't it? So this is the derivative of this function, so the left hand side. So if I move this one on the right hand side, that means it's going to be plus R over L times IL. That's the function that I estimated. So A times cosine omega t plus theta. It says equal to 1 over L. This source function, that's that source function. So that means small a times cosine omega t plus phi. So the left hand side must be equal to right hand side. In this case we called identical. Left hand side should be identical to the right hand side. Identical means this is true, left hand side equal right hand side for any t value. So we show it like that. So if you look at this now, you can multiply it, all of them by L. So let me do it. Maybe I should write once again. Minus A L, maybe L A. Make it a bit nice looking type. L A omega. If I put it, oh, okay, write it differently. So I'm going to if I multiply all these terms with the same L, so L is going to be a coefficient here. If I put the A parenthesis, my left hand side, minus A is equal minus A. After the multiplication, omega L sine omega t plus theta, and make this minus, put the minus, transfer this minus inside. So it's going to be this minus theta plus, we multiplied with L, what is left is R and A is outside, so the R times cosine omega t plus theta is identical to A times cosine omega t plus phi. Right? Okay, what we're going to do, we're going to do something different here. If I say that I'm going to divide these two terms by r square omega square L square square root of it. So, and this r divided by r square omega square L square, and multiply this a with this r square omega square L square square root of it. So if you do the multiplication, this gives you 1, this multiplication gives you 1, so nothing would change. But what happened here, if you look at this, maybe change the color here, make it this. Look at this now, and this. Oh, sorry, so this should have been coming like that. So if I draw now a triangle here, and this sine omega L and R, and this hypotenuse becomes r square omega square L square square root of it. So we know that. If you consider that alpha now, so cos alpha is equal r over r square omega square L square square root of it, and sin alpha is equal omega L over r square omega square L square. Fine. So if I transfer it to this one, this is going to be sin alpha, and this is cosine alpha. So trigonomically, this is equal to what? I will write it here. Go back to square root r square omega square L square times a. Inside that, this is going to be 2 sine multiplication, 2 cos multiplication is equal cos omega t plus theta plus alpha is this, is equal a times, is identical cos omega t plus phi. From that, we could say that there are 2 cosine functions, left hand side and right hand side. The coefficient of this cosine should be the same as the coefficient of the right hand side in order to have it identical. So it is going to be now a. From that I can say that capital A is equal a over small a over r square omega square L square. And this angle here must be the same as this angle, so theta plus alpha is equal phi. From that, phi theta is equal phi minus alpha. What is alpha? So since this is if you look at this here, tangent alpha is equal omega L over r, and alpha is equal arc tangent omega L over r. So I can write that theta now is equal phi minus arc tangent omega L over r. What we have done, I'll show you. So we said we are going to calculate this capital A, and we are going to calculate this theta. So the capital A we just calculated here. In terms of what? In terms of the source magnitude and the element parameters in the circuit. And we also calculate that theta here, that theta, and we have calculated this parameter as well. In terms of the source angle phase, that's phi, and the element parameters L and R, and the omega, which is the frequency of our source. So that is the part. So I calculated the 2 parameters that I needed to calculate. So I can say that my particular solution now, here, write it in green, ILT particular is equal to capital A becomes this, cosine omega t plus phi minus arc tangent omega L over r. So here you are. That is what we are looking for. So conclusion, that is the homogeneous solution. here. That's the particular solution. So addition of those two gives you the general solution. Why we explain all that? We said if we source the if we change the independent voltage source from a DC to AC, what will change is that particular solution. How it changed, you could see it. If it were DC, this particular solution was going to be a DC, a constant. In this case, we calculated two parameters here. Now we can transfer it. Now we did the solution in general. We transfer this general solution, that means parametric solution, to the numerical solution. Let's do this now. Come to this one. Here are. We've got this differential equation. This is our AC source, and the particular solution, what we just found, and that's the homogeneous solution. If you replace the numerical values with this one, for example, the independent voltage source, AC source angle has been chosen 0 to make it a bit simpler. So if you put these values in, so it's going to be, our solution, particular solution is going to be this, and homogeneous solution is going to be this. As I said before, calculation of that C is going to be done at the end of our calculation. That means by using the initial condition. If we use the initial condition here, T equal to 0, then this current, then general solution current is going to be 0.5 here. C, when T equals 0, this term becomes 1, C times 1, plus this cosine value when T equals to 0. That means 0.2 times cosine minus 2.86 degree gives you that 0.199. So C is almost equal to 0.3. So our general solution, numerical solution, is this. So this solution, if you look at this solution now, what is this solution? This term, since it is exponentially decreasing function, it's going to disappear after a few minutes, or a few seconds, let's say, because exponentially decreasing function, there is a t here. Make it a bit more, so there is a t here. So this term is going to disappear, that's why it is called transient solution. This disappears. This solution here, in general solution, that part here, is called sinusoidal steady solution, SSS. That is the one that we are going to observe forever. This is going to disappear, that's why it is called transient solution, and this is the steady solution. So if you do the same thing for by using the protos, so this is our circuit, the protos analysis of this circuit, so this element current is this. So if you see it here, at the beginning there is a strange shape here. That strange shape comes from, here are, to make it exactly the same, comes from this transient term. That's the transient term here. After that, we are going to observe this function, so this function is this function. So steady solution is that, and at the beginning you see summation of those two, so mainly this part is effective. You see that exponential decreasing coming from that point. Why it is coming from that point? Because the initial condition is 0.5. Here you are, initial condition 0.5. Amp means 500 milliamp. So it starts from that, goes directly, immediately down here, and then it becomes a sinusoidal function, which is that function. So what happens if we change the R and L values? This is what happened here. In here, L value is 0.5. In here, it is 0.1. That means 5 times reduced, that is, isn't it? L value. In here, R value kept as it is. So the time constant is, by definition, is L over R. So there is a time constant for this case, the green one, and this is red one, and the third one is the time constant for the that blue one is the time constant of this circuit. This one has got the same L value as the original circuit, and the resistor value has been reduced. In here, L value has been reduced, kept the other value as the original one. In here, R reduced, and L kept it as the original one. So what we are doing by changing L and R values, we are changing the time constants here. So it is 500 microsecond, 100 microsecond, and 1 millisecond. So that means the time constant, so that beginning becomes a bit shifted towards the right way according to the time constant value. Afterwards, if you see this blue one, the magnitude of the blue signals is higher than the other ones. What could be the reason? So if you look at this solution, it's not here, but you could see the solution here in general. Here are. When the R is reduced, that means this coefficient increases that, because this is in the denominator decrease, so this whole ratio is increased. So this is what we are expecting though. So R value reduced means amplitude increases. What we observe here is this. But L is not that much effective, so you can tell us why is that, because L is multiplied with a coefficient which is that angular frequency. That angular frequency is in the range is 100, square of it 10,000. Therefore L is not that much effective, but R is effective, so you can observe it in here. So if you look at the whole scenery here, what we have done, so you could see that we are examining the first order differential equations when this independent source is a DC source in here, and when the independent source in AC source here. So we examined this one. That is the end of this video then. Stop.